Kevin Walker, and he wanted to explain the beautiful picture from before, and then talk about how to develop some state sums for general defect TQFTs.
Okay, maybe I'll save the picture explanation for the end if there's time. Yeah, thanks to the organizers. It's been a fun program, etc. There at some parts, and I'll indicate in the talk, parts of this are joint with David Reuter. Okay, so here's the outline of the talk. The goal is to discuss defect TQFTs, and in particular the top part, this state sum path integral, in a general context, so in any dimension, any pattern of details. But first I'm going to go through in parts 1, 2, and 3 the part that does not involve defects, and then we'll see in parts 4, 5, and 6 that doing it with defects is really not much additional work. And then if there's time at the end, maybe some applications of things you can do with, state sum formulas or for path integrals for defect TQFTs. And yeah, so I guess I'll just jump right in. And so before we get to part 1, though, I wanted to kind of set a context, because I think this is a pretty diverse audience, and I think that maybe for 75% of the audience, I'm going to be too abstract, and for the remaining 25%, I won't be nearly abstract enough, and so I'm maybe in some no man's land in the middle. But I just wanted to say how the approach we're taking to TQFTs fits in a larger context. So if you're a physicist, like back in the late 1980s, if you're Ed Witten, this is what a TQFT is. Oh, I've got my pointer. So, the initial ingredients, you have some fields, you have an action, you have a measure, and putting those ingredients together, you can do a path integral. And from this path integral, you can produce a lot of stuff. One thing you produce is a sort of Bordism infunctor, assigning things to manifolds that behave well in a gluing. But there's also asymptotic expansion formulas, which involve, varying the action and looking at things and perturbative techniques, etc. Transposed. Okay, so mathematicians don't want to do it this way because we don't know how to make sense of the path integral as an integral with a measure. So Tia's Siegel idea is to just forget about most of this stuff and take this as the starting point. So we start with a Bordism infunctor that I probably started with Siegel in a CFT context, and then Tia wrote a very influential article in 1988 or so. And then initially that was just supposed to be a 2-level structure, path integral Hilbert space, but it was gradually realized. I think some of the earlier people were Quinn and Fried separately, that it should extend all the way down, and we should assign fancier algebraic invariants to lower dimensional manifolds. So that's most mathematicians, when they think about TQFT, they're probably taking this point of view. So I want to propose something slightly different, but still kind of compatible, which is we didn't have to cross out everything here. In particular, these fields. Say more about them in a moment, but that's a perfectly well-defined mathematical object, just like you assign to a manifold, maps of that manifold into some target space or string diagrams or connections, and those are easy to axiomatize. And then if we still don't know how to make sense of this measure, but we can just treat the path integral of these two manifolds as a black box. Now they're both an n+1 dimensional manifold, but if we think of it as a map from the n ball to the n ball, that kind of gives us local relations on fields. And then most of the talk is going to be about, if we think of it as a map from the empty manifold to the n sphere, this is the seed for constructing a path integral and eventually the state sums. So oh yeah. Okay, so the epsilon and that terminology, it's sort of a joke. I got it from Chris Douglas. if we do, yeah, let me, I'll explain it on the next slide, actually. Well, it's just the physicists wouldn't endorse this point of view. I'm just saying, I'm replacing one speaker with another speaker. So the epsilon basically refers to diffeomorphisms acting on N manifolds, and that can be thought of as a very thin N+1 dimensional manifold. I think I initially called it like, N+1/2 dimensional TQFTs, but Chris Douglas said epsilon's better than 1/2, and he was right. So I'm sticking with that terminology. Okay, and I should also say that this topic is full of very fiddly details, and even though I've got like a long time to talk, I don't want to get into. I think I've cut a lot of details out of the talk, and there's still probably too many left. So I'm just trying to give you, overall picture. So when I said these field functors are easy to axiomatize, what do I mean by that? So we could assign to a manifold. The main example in this talk will be we assign to a manifold the string diagrams drawn on that manifold. And if we're and we just think of that as a set, if we're in dimension lower than n, and in dimension n, and n is the space dimension, space-time dimension. Dimension n, we linearize and impose some relations. And so if you have, your preferred way of thinking about n categories, and they're pivotal in the right sense, then you can probably produce string diagrams, and and then your string diagram functor will fit into the formulas I'm talking about. Another example is we could assign to a manifold X, sort of a sigma model that maps from X to a target space. And you'll notice that if you think about how these things behave under gluing and restriction to boundary, they have very similar formal properties. So you write down what those properties are, and those become axioms for fields. And then if you restrict your manifolds just to being balls, you can think of them as axioms for n categories. Yeah. Okay. Oh, K is the dimension. I'm sorry. Yeah. So this is a topologist. So but often I'll name manifolds by a capital letter, and the first time they appear, I put an exponent to tell you what dimension it is. Yeah, it's a bizarre convention, but I grew up with it, and sorry, but yeah, it makes no sense if you don't already know the convention. No, generalized string diagram. Yeah, so dual to a pasting diagram for a category. So foams, webs, that kind of thing. Thanks. Okay, so now we're finally at part one. So with this, I don't want to dwell on the n+1 dimensional part of the theory. I'm sort of regarding that as easy, and then we're looking at extending beyond that. But it is we have to talk about it a little bit. So the construction is given one of these functors from the previous slides, in particular string diagrams, we can take C-linear combinations of the string diagrams and mod out by local relations. Secretly, the local relations are sort of path integral project. You think of it as the effect of a Bordism from a disk. And more formally, one could form a big colimit diagram where each vertex in the diagram is some way of chopping your manifold into balls. And then I want to assign a vector space to each of these things, and the way you have to decorate the interfaces with appropriate boundary conditions for the string diagrams, and then you get a vector space for each ball, and you tensor them all together. And then each of these maps involves gluing two balls together, and your category information tells you how to do that. And so you have a functor from this thing in the vector spaces, and you take the colimit of that functor, and that's sort of the fancy way to do the scheme module. It would describe the Hilbert space, or the pre. Yeah. This is topological from the very start.
Right. TQFT means
Oh, okay. Yeah, sure.
Is that right?
Well, I never use words like RG fixed point, but yeah, this is there's no correlation links. This is topological from the very start.
Anything that is in that, let's say, improvement scale, like that,
I see. Yeah, and I think I'm taking more of a more purist approach to TQFTs, but okay. So I've got a manifold M, and in this picture, the M is an annulus, and then each of these pictures is a way of dividing the annulus into disks, two-dimensional balls, and then. I mean, yeah, this isn't going to be important for the rest of the talk, but I'll finish the explanation. But if it's confusing, that won't affect comprehension of future slides. This is more a remark for the mathematicians in the audience. And then if I, again, think of some two-dimensional string net, if I specify a boundary condition on all these blue lines, then I have the vector space of string diagrams drawn in that disk with that boundary that I can assign to each disk. And then I can tensor them together, and I get some vector space assigned to this picture. And then the orange arrows, the maps, are going from here to here. What I've done is I've sort of glued this disk and this disk together by erasing that. And some of the, if the sort of a fundamental part of an N category is a composition operation, so that tells you. Yeah. Maybe it's too subtle. And so, yeah, so this, I think if you're a physicist, you should ignore this. And if you're a mathematician, it might make you, may or may not make you happy to see something like that. Whenever we can use words like co-limit, we make some people happy. Yes. Yes, that's right. These lines are just ways of chopping up the annulus. I think implicit in the picture, but not drawn, is some kind of string net. And I haven't drawn that in this figure. But this, it ends up giving the same answer as this top thing, which is much easier to understand. Oh, the B is an outer boundary condition on the annulus. Yeah, sorry. I should have, yeah, so B is a boundary condition. So if I have like a manifold with boundary and I want to draw string net pictures on it, I fix what they are on the boundary. No, this outer boundary is the same in all pictures. Yes, let me, so here's an annulus, and my B might be, 2 dots there and 4 string endpoints here. And then a diagram that's compatible with that boundary condition would look like, this or something. And then I can try to compute this vector space by, chopping the annulus up into pieces. And that creates, more boundary conditions I have to keep track of. But those, vary from node to node, whereas these on the outer ones, it's the same.
But the action is an action.
That's right. Sorry, yeah, it's a very parsimonious picture. And again, it was intended just to remind, maybe no one in the audience was familiar with this kind of construction, so it didn't help anybody. But it just sort of, concretely what it means is in here I can draw various things, and if I start with the same vector here and map with this arrow versus that arrow, they might look different here, and the co-limit means I identify them. So it's somehow the things that are, it's in some sense a flat connection over this combinatorial data. Okay, so that's sort of a string net construction of a Hilbert space. What about if we have a manifold of dimension n-1? Again, we have a boundary condition, which I'm going to, they're important, but I'm not going to draw them through most of the talk. And we can construct a category. So the objects are boundary conditions on, think of them as the top and the bottom of the cylinder. The morphisms are the vector space from the previous slide done on the cylinder. And then the composition in the category is gluing things together. And so, for example, in the dimension that I've drawn, the representations of this category would be the anion types for the theory for doing something 2 + 1 dimensional. And more generally, if you're a condensed matter person, you should think of the representations of this category as excitations whose boundary looks like y in -1 manifold. So for example, if we had a 3D system and we had a loop light excitation, y would be a torus.
We are talking about 2 + 1
Yes. For me, n is 2, and by which I mean 2 + 1 dimensional TQFT. So n is my space dimension, not a space-time dimension. Okay, and so the general thing, which won't be necessary this talk, but if you want to extend all the way down to points, then we would like to construct a K category for an n-k manifold. And the J morphisms are just to take your manifold, cross with a ball, and do the obvious construction on that. And composition is given by gluing. There are lots of fiddly details one has to verify there, but this is the case where K is equal to 1. And so we had the original manifold Y, but we also looked at Y cross I, and then these things kind of assembled into a 1 category, but we can do that to make a K category if we wanted to. Okay, so with that, and again, I remember, we haven't introduced defects yet, but we'll do it in a similar way. To go from, what about the path integral? So the construction of the previous slide, I didn't have to choose any handle decomposition or triangulation of my manifold. So it was obviously a sort of diffeomorphism invariant or coherent invariance for manifolds. But to go to the top dimension, I don't know how to do it that way. Like if we could actually do a path integral, then it would obviously have very properties. We don't know how to do the path integral as an integral. So we're going to do something combinatorial, still call it an integral. And so what do we want? For each n + 1 dimensional manifold, we want to map from this vector space associated to the boundary to the complex numbers. So this is in some sense a pre-dual to the Hilbert space. And furthermore, we want to be able to switch our boundaries from being incoming to outcoming. So there's an inner product on these spaces defined by evaluating the path integral on manifold cross I. And we want that to be a non-degenerate inner product. And so in particular, that might force these spaces to be finite dimensional. The previous part 1 works for a very general class of inputs, like rep Q of G for generic Q. But if we want to do the path integral, then we put some much more restrictive requirements on the inputs. Okay, so how do we do this? Well, what's the simplest path integral we might want? It's the path integral of the n-ball, which is a map from this space to the complex numbers. So we just take a guess, make some ansatz for what that might be. In this context, this is often called a zero handle, but it's again where we have all the boundary is either incoming or outcoming, going depending on your convention. And one can also think of this as a trace on the category. So now we're, instead of just a plain pivotal in category, you have a Calabi-Yau or category or something like that. So now we can define an inner product on string diagrams on an n-ball by gluing 2 of them together, and then we get something in here, and then we evaluate. So this inner product may or may not be non-degenerate, but if it is non-degenerate, that allows us to compute the path integral of this slightly more complicated manifold, circle across an n-ball, the answer from here to here. And now using that, we can, again, cut this, the boundary, this manifold here into two pieces. A ball, two different balls calls this one. It's a detail I am suppressing, but it basically when you glue things at this path integral dimension, the sort of most direct way to do it is to, I guess it's this idea from QFT that if we chop something in half, we insert like a space. I mean states. So here are two manifolds, and I've chopped them apart, and I need to insert something here and here, and I do sum of EI tensor EI over for some basis. And so, but does this exist as a finite sum? Well, there's a dual pairing associated here, and if that has a co-pairing, that is equivalent to this existing. So that's roughly the idea. Okay, but that yes, I cut this into, say, two different balls, and I know how to compute each of those because now I've got the manifold that's up here, and I just need to glue them together. So it's or one. So we start out with S1 cross Bn. We maybe divide it into two pieces. And now, we're kind of in this situation. And so we already know how to compute that. We know how to compute that, but we don't, if we knew what to stick into this, new boundary that I've created. And the thing you stick in there is basically the co-pairing to this pairing. So it's a sum over basis vectors like that.
First line supporters from the sphere to the empty set. And are you cutting the ball in half to get to, and then the boundary of that boundary sphere becomes two hemispheres? Is that what we're saying?
Yes. Yes.
And then what do you do in the arrow in the middle?
What I do is what I was talking about right here. So this is Bn. And what I need is some kind of orthogonal basis for the skein space of Bn. And that's what this co-pairing is. I'm sorry. I am trying to fit into my allotted time, and that was a detail I chose to suppress, but maybe I shouldn't have. It's because it is an important detail for the rest of it. Yeah, well, the boundary could be cut as well, and you have to keep track of that. Yeah, yeah, we're considering more. Yeah, this is a newbie each time they live in. If we're doing closed manifolds, it might disappear altogether. Okay, so this just continues, and eventually we've computed quite a lot of the theory. I'm going to emphasize, we made a choice on the path integral of the n+1 ball, the zero handle, but after that we had no choice, and we've sort of now learned how to compute handle attachments for handles of any index. So the non-degenerate, on the previous slide, I said I had a non-degenerate inner product for this manifold. This manifold is the attaching region for a k+1 handle. And so every manifold has a handle decomposition. So I can, in many different ways, compute the path integral of an arbitrary manifold now. But how do I know I get the same answer? So to actually prove it's well defined, you have to show that different handle decompositions give the same answer. And the main relation you have to show is that if you first add this k handle and then add a canceling k plus 1 handle, that's the same as doing nothing at all. And so the theorem in this form from a long time ago is if we make some pretty strong assumptions, like all these skein spaces are finite dimensional and all the categories we see are semi-simple, and furthermore, if this initial choice induces inner products on the in-ball, which are non-degenerate, then the cancellation holds at all indices, and there is a unique path integral which starts out with this initial choice H0, the zero handle. And then a more recent theorem, this is joint with David Reuter. It makes fewer assumptions, so we don't make any assumption about semi-simplicity or even that the categories are unital. But then we have to check each of these pairings individually. We don't, in the first one, just once the first pairing is non-degenerate, all the others are, because we can write out explicit bases and check that. Here we check individually that each pairing is non-degenerate, but if they are, again, we have a unique path interval. When I started preparing the slides, I wasn't sure that this extended, so I think that the talk is much more oriented around this, but I thought this was more, in the course of preparing the slides, I realized that this version will also generalize to defects without much problem. Okay. An example. Well, so yeah. So this like theorem 1 would lead to things like Tarai-Vero TQFT. But this one, something that's not handled by the previous case. Is that what you're after? Yeah. So the motivation for working on this, there's a long literature on non-semi-simple Reshetik and Turayev-like invariants, and also Tarai-Vero-like invariants. It involves taking quantum, a small quantum group, and you look at just the projective representations, and what this basically, the punchline to or an application of this theorem is that those theories actually fit into the same framework as things like Tarai-Vero. So that was somehow the goal when we started thinking about this. So it would take a while to describe those examples explicitly, but they are, strictly different from the usual Reshetik and Tarai or Tarai-Vero type theories. Which goal? Yeah, that's, well, I think there's a few details to be checked, but yeah, that's written down hopefully on the archive within a few weeks. So if that's what you meant by HTM. Okay, this is, yeah.
Maybe just roughly, because it's not in the archive, but so these non-semi-similar type constructions don't get a filter.
Yeah, so one thing, when I say Reshetik and Tarai, what I really mean is Crane-Yetter, the higher dimensional theory, and then I derive Reshetik and Tarai stuff at the end. So when you said I didn't know whether you mean not fully extended or just restrictions on like incoming or outgoing boundary being non-true.
I don't remember all the names, but Gia and Ingo is one of the authors.
Exactly.
So this construction as a symmetric Noether functor on the bordism category that is not rigid, does that appear as a theory as itself here or at the boundary of a 4D?
It appears at the boundary of a 4D theory. Okay, so I'm running behind on time, so this is just saying something about how one might prove it. It basically comes down to associativity of gluing. Like what we want to prove is that the top arrow is trivial. We first attach a K handle and then we attach a K plus 1 handle. But if we reorder our gluings, then attaching the K+1 handle first is really just gluing a boundary collar. And then attaching the K handle to that is, again, boundary collar. These sort of maps I claim are sort of obviously the identity, and because things are associative, it means the top map's the identity. Okay, so now the final step is, now once we've know how to do a path integral, we can try to turn that into a state sum. I should note that this is historically backwards. Historically, people wrote down state sums first, and then they, sort of described it as a 2-level TQFT, and then after a while realized it could maybe be fully extended, but we're preferring to go in the other direction. So in attaching a handle, similar to this picture I drew on the board, I have to plug in some kind of orthogonal basis where I'm attaching it. And so what is an orthogonal basis of the space? There's a notion of a minimal morphism, and let's see, I think maybe I'll draw something on the board. So suppose my attaching region looks something like a 2-sphere, perhaps thickened up, and I have string nets drawn on that. I'm looking for a basis of this scheme module. Well, any picture, I can choose my favorite region. Maybe there's some label there, and then after rearranging, it just looks like the whole thing's colored by A, and then everything else gets, shrunk to some point. So certainly diagrams like this span the two-sphere space, but we want a basis, not a spanning set. If I had instead started here with some different two-morphism, I could have gotten a similar picture where instead of an A, it's a B. And you might ask, okay, how are we going to turn that spanning set into a basis? Well, first we assume that this is a very simple morphism, that it's higher into morphism algebra, is a simple algebra. And then we do an equivalence relation, which means if they ever share an n-1 morphism. So this idea, I think, first appeared in Douglas and Reuter around 2018. I think it's not a very complicated idea, but I think it's what held up, one of the things that held up progress for higher dimensional state sums. Okay, and so with that observation about bases in hand, now we can take a handle decomposition and just write something down. And it looks like this. So what are the ingredients? One important ingredient is I'm summing over a space of labelings of my handle decomposition. And those labelings correspond to that basis choice, this kind of choice for each handle as we go down. And so this is just a way of writing an orthogonal basis for that handle attachment region. And it's hierarchical. So I first choose the labels corresponding to high index handles, and then that gives me boundary data for the next round of handles, et cetera. And then for each handle, if again, let's draw the handle attachment. I've got the rest of the manifold, which I'll subdivide later, but what are the contributions of this part and the gluing? Well, the contribution of this part is just an evaluation over the entire boundary of the handle of that. I've written the boundary of handle and beta is some labeling by morphism. So this is some string diagram, and the evaluation is a 0 handle that we started the induction with. And then there's some correction factors involved with this gluing, so I'm just calling that N. And N should be thought of as somehow the norm squared of this morphism. But there's a kind of recursive formula if you're more category minded and don't want to think about topology. You can write norms of higher morphisms in terms of norms of lower ones. Just to give an example what these things are, the norm of an object in a 1 category is just the dimension of its endomorphisms algebra, which is, if it's minimal, is always 1-dimensional. if we're doing things bosonically, but could be 2 if it's fermionic. The 2 norm is a global dimension, which is a familiar constant from studying tensor categories. And then this one is kind of weird. So when I was first working this out, I came to this and I thought I'd never seen an expression like that before, so probably I made a mistake or something like that. It looked too weird, but then I came across this Douglas-Reuter paper, which I was unaware of, and they wrote down the same thing. And so I thought, aha, it's not a mistake. You really do need something. This is somehow, if you're dealing with 3 categories, this is the analog of a global dimension. Some of the reciprocal of the global dimensions of the blocks 3 category. Okay, so using up about half my time, I've gotten through manifolds without defects. So now we want to go through that again and see how we have to change things to make it work with defects. Oh, I'm sorry. This expression on the previous, that may seem too abstract and general to actually get anything concrete out of it. But the point of this slide, this is excerpts from a paper, is that it's pretty easy to turn, this expression into like Tarai-Vero, for example, just by computing, all of these terms can be computed fairly explicitly. So you can get concrete things like the Tarai-Vero state sum or the Douglas-Reuter state sum. Okay, finally, defects. So what do we mean by defect? I don't think physicists ever worry about this, but if you're a mathematician, you might wonder, what kinds of stratifications or cell complexes are allowed, and we just take things that are closed under taking cones and products. That's an old idea, and I think everyone who works in the subject uses the same answer. Oh, that's just the name for a theory that doesn't have a path interval. But so now we're going, so it means you've got, what the epsilon means is we've got all the invariants that we would expect for manifolds of dimension n and lower, but then we also have diffeomorphism acting in dimension n, and that can be thought of as a mapping cylinder or a very thin n plus 1 dimensional. So we go just epsilon toward, well, we can define the path interval for a 4 manifold if it's very thin, basically.
Typically, people use epsilon for regularizing theory, but you do it for a different reason.
Yeah, completely different reason. Sorry, I should. Okay, so this vibration. So the thing to think of is maybe if n is equal to 3, I have some line which might have a cross section looking like 3 different sheets. Draw it again. And so here the normal fiber would be equal to a disk divided like that. And this could be higher dimensional, and this stratum could also be higher dimensional. Yeah, I'm coming to that. Yeah, well, so first that slide was about the undecorated case. Okay, so now how do we decorate them? And I think rather than jumping to the general definition, I'm going to give examples first for small n. So if n equals 1, then unsurprisingly, the regions are decorated by 1 categories, algebras if you prefer, and the points in this one-dimensional example, n plus one-dimensional example, are bimodules. When n equals 2, again, it's mostly unsurprising. The regions are labeled by pivotal 2 categories, for fusion categories, something like that. So that's the usual ingredients for a 2 plus 1 dimensional TQFT. The codimension 1 things are labeled by bimodule categories. And But I think, different authors might disagree about, what do we label the